For the first half of this lecture, we're going to finish the discussion of the matching relation for the two-jet current. This was our chapter. And remember, can we lower a bit? Okay. Remember the relation we had written down. So basically what we want to do is we want to have an external vector current, for instance, a virtual photon. You can do the same thing for axial vector or other currents. And we had, in a two-jet configuration, we want to describe this in terms of collinear and anticollinear fields. And last time we had written down a gauge invariant expression for this, which involves anticollinear and collinear fields and their corresponding Wilson lines. And the Wilson lines are needed for gauge invariance. And this was the expression we found. And remember that we also found that these Wilson lines account in a very non-trivial way for infinitely many tree-level hard matching contributions. So whenever we have diagrams of the type that we have a collinear and an anticollinear quark, and now, for example, we attach a collinear gluon to this anticollinear quark, that gives a hard propagator, which in the EFT is integrated out, and therefore the EFT operator has arbitrary numbers of collinear and anticollinear gluons at tree level, at leading power, and they are all described by these Wilson lines. Now, if we go beyond tree level, this operator will also receive a Wilson coefficient. One calls this quantity C sub V for the vector current, and we'll see that this is a function of Q squared. It will also be a function of the scale at which this current is renormalized. And Q square, remember, is the, so minus a little q square is big Q square, is the momentum carried by the current. It's not at all it's an interesting question how a matching coefficient in such a relation can depend on the hard scale Q square. Of course, Q square is the hard scale. It should depend on Q square, but Q square in reality is related to the momenta of particles in the effective theory. So normally the Wilson coefficients do not depend on the kinematics in the low energy effective theory. They depend on some heavy masses. But in this case, they somehow need to depend on Q square, and we'll see how this dependence arises. In fact, the answer how this dependence arises is related to another puzzle we had discussed already. And in fact, when I wrote down this operator last time, you could have insisted that there should also be other operators I can write down, because remember that I told you that there are components of the collinear gluon field which are unsuppressed. For the collinear gluon field, it's n bar dot A. For the anticollinear gluon field, it's n dot A anticollinear. These fields have order 1 power counting. So in principle, I told you, give me any operator in SCET, and I can write down infinitely many operators where I just add such gluon fields, okay? Now, of course, you have to do that in a gauge invariant way, but you can easily see that the following infinite set of operators were similar to what's written up there, but with additional insertions of these fields in the form of covariant derivatives. Let me dagger this so it acts on the collinear field and then raise it to the mth power. and to the, no, M1 and M2, sorry, M1 and M2. You see, these are infinitely many operators which I can define a gauge invariant, and they contain more and more fields, but all of these fields they contain are order 1. So even though they have higher dimension in terms of mass dimension, they are not suppressed in terms of lambda. I would have to compensate somehow for the mass dimension by adding powers of 1 over q square, but these are the large derivatives, so they compensate for this 1 over q square suppression. And in fact, this looks like a problem because we had this nice matching relation, but in reality, and we'll also see that this relation at the end of the day is correct, but in reality, we could have written down any of these infinitely many operators, and it would have the same correct properties to describe this current in the effective theory. So here for any M1, M2, any natural number including 0 would have been perfectly fine. Now, how are we going to deal with this problem? So first of all, we use our beloved relation that the Wilson lines are annihilated by corresponding covariant derivatives. So remember, there were many ways of writing these relations, but the most useful one for now is the statement that if we have n bar dot d collinear acting on a collinear Wilson line, we get 0 if it acts on the Wilson line. If we see this as a differential operator that can only act on things that stand to the right of this expression, then we can pull this through. And we simply get an ordinary derivative because then the two Wilson lines cancel, right? If it acts strictly on the Wilson line, it gives 0. But if there are other fields on the right-hand side, then the ordinary part of the derivative acts on the other fields. So we have this identity, and we have the corresponding identity in the anticollinear sector. And I can use this identity to rewrite this operator, because basically it tells me if we commute a covariant derivative with a Wilson line, it turns into an ordinary derivative. So basically, I can pull these derivative operators out and write this operator in the following form: C bar n bar, WC bar at 0. And now I have ordinary derivatives. And instead of dagger for ordinary derivatives, let me write this as n dot del acting to the left. And this is to the power m1. Then we have gamma mu perp. And here we have n bar dot ordinary derivative m2 times acting on WC dagger C n at 0. And let me call these operators O, M1, M2. So the operator O00 is the one that we have up there, but I'm basically telling you there's an infinite number of operators which we could have. So in other words, more generally, we should allow for all of these operators, okay? So the matching relation that we should write instead of this one is really the following. We should allow an infinite sum over M1 and M2, 0 to infinity. Some matching coefficients, let me call them little c, M1, M2. And all of these, let me just write it like this, times this operator. And then the term where both indices are 0 is this operator, but more generally, this is the matching relation that we should have written, really. Now, you see here that we sum over powers of derivative. You know infinite sums over powers of derivatives. That is what we usually call Taylor expansions, okay? So I claim that this double sum can also be recast as a Taylor expansion. So an equivalent form of writing this, I claim, and we'll prove it in a second. An equivalent form is the following, that I say my current matches onto a double integral from minus infinity to plus infinity some function C tilde of T1 and T2, and now C n bar WC bar at position T1n, gamma mu perp WC dagger Cn at position T2 n bar. So once again, we see non-local structures appearing. We have the collinear fields now spread out on the light cone along n bar, like for the collinear Wilson line. And we have the anticollinear fields spread out on the light cone in the n direction, like the anticollinear Wilson line is also going in this direction. So we just also now take the quark fields and move them on the same light cone. And this is the structure that we also saw in the SCET Lagrangian. In the second term, we had WC integrated along the n bar light cone. Now, how can you see that this and this is equivalent? Let's prove it. So basically, we use the Taylor theorem or Taylor expansion, I don't know. Use Taylor series. What is a Taylor series? Well, if I have a function f of t n bar, I can write it as an exponential of t n bar times a derivative with respect to x of a function f of x. And then after I take all these derivatives, I set f equal to 0. Okay? So basically, this is the, of course, in quantum mechanics, this is the translation operator. It takes this function and it translates its argument by an amount t n bar. So and we get the function not at 0, but at t n bar. Okay? And of course, this exponential, the translation operator, I can write as a Taylor series. I can write as m from 0 to infinity, t to the power m over m factorial, times n bar dot derivative to the power m times f at 0. And you see this smells very much like what we have here, except we have a double Taylor series in this variable and in this variable, right? So I hope it's clear that if we use this Taylor theorem for this function to write it as a sum over m, like there, with m derivatives acting on the function at 0, we get an expression that is exactly of this type. And what you find is that the coefficients, which are called Cm1, m2, are nothing but the following integrals: dt1 minus infinity to plus infinity, dt2 minus infinity to plus infinity. This coefficient, which I called Cf t1 Cv, sorry, twiddle t1 t2, and now minus I t1 to the m1 minus I T2 to the M2 over M1 factorial M2 factorial. In other words, these two formulas are really completely equivalent. I can work with this form, I can work with this form. I have a coefficient here depending on the two variables. I have an infinite number of coefficients here depending on M1 and 2, and this is how they are related. Okay, so these coefficients are really simply integrals of the original coefficients. Yeah? Always this twist coming back to me. I think this is a Taylor expansion. It's again, yes, it's related to the twist expansion, but yeah. Oh, I just wanted to be general. I mean, if this function happens only to take values at positive t, then in essence it runs from 0 to infinity. I don't want to assume anything. I want to be completely general. I mean, I can always write it like this, and then maybe this function has support only in a finite range of parameters, but the most general relation is this. Okay, so I hope you agree that these two things are equivalent. So now we have a new matching relation instead of this one, where I put the fields at 0. The expression is now more non-local. It was already non-local anyway because of the Wilson lines, but no, now it's also non-local in the sense of the quark fields. Okay, now there's another nice thing which is related to the same Fourier trick that I used here. We can now use that the total momenta, so the total, not the individual, but the total collinear and anticollinear momenta are fixed by kinematics. What do I mean with that? I mean with that, if I do virtual photon to two jets, and I know the center of mass energy, then I know the energy of the two jets, simply by energy momentum conservation. And let me only talk about the large components of these momenta, because this is what we'll need. And let me call these total jet momenta calligraphic P with the subscript collinear for jet 1, and for jet 2 the large component is n dot calligraphic P C bar. I could also call them P jet 1 and P jet 2, but I want to be a bit more generic and just say that this is the total momentum in the collinear sector, this is the total momentum in the anticollinear sector, and I only worry about the large components. These are always known, because when I introduce soft collinear effective theory, it's always because I have a situation where in some scattering or decay, I have a final state consisting of energetic particles. It could be E plus or minus to two jets. It could also be meson decay into a jet of light particles. But in all these cases, the energy of that jet is determined by the mass of the decaying object, basically. So let me just use that I know really what these momenta are. And now I do the following trick yet again. Now I use the fact that, well, it's almost like doing the same thing again. So you see, For instance, let's take this. I take a W dagger Cn at T2 n bar. I can again use the translation operator, but I'm now writing this in terms of these momenta because the translation operator in quantum mechanics is the momentum operator, okay? So, of course, this derivative operator is h bar over, no, the momentum is h bar over I times the derivative operator. So the derivative operator is minus I times the momentum operator. And that momentum carried by that field is known and is equal to this quantity here. So let me just write this known total momentum, and then I can translate the field back to position 0. So this is just, again, using translational invariance. Normally there is a derivative here, but I know what the derivative does. It picks out the total momentum carried by these collinear, by all collinear fields. And I know that momentum from kinematics. I call it capital P. And I do the same for the anticollinear sector. And now we get back to a formula that gets closer to the original formula. Now we get integral over T1, integral over T2, both from minus to plus infinity, C tilde V of T1 and T2, e to the I T1 n dot P anticollinear, e to the minus I T2 n bar dot P collinear times C bar n bar W C bar at 0 now, gamma mu perp W dagger C C n at 0. Okay, and now what's this? How do we call if we have a function here and we take an integral of this type? What do we get? The Fourier transform, right? So this is the double Fourier transform of our C tilde, which originally depended on the two position variables, T1, T2. Now we take the Fourier transform, we get the coefficient in momentum space now. What does it depend on in momentum space? Well, you see it from the face. It will depend on n dot p and n bar dot p. Okay? So this is now, of course, I'm going to call this now C without the tilde, and it will be a function of n dot total anticollinear momentum, n bar dot total collinear momentum. And now we're almost there. Now we remember that Anish has this beautiful paper about reparametrization invariance, and it told us that things have to be invariant under rescalings of n and n bar with opposite factors. Okay, so if we rescale n to alpha n and n bar to alpha 1 over alpha n bar, things have to be invariant. If you look at this coefficient, if this should be invariant under this rescaling, what can you conclude about the dependence on the two variables that this function in general has? It can only depend on the product. Okay, so this is by reparametrization invariance. We know this function can only be a function of the product. This is typically how we use reparametrization invariance of type 3. It's always simple, the consequences, but it's non-trivial. It tells you this function, which depends in general on two variables, is really a function only on one variable, which is the product. Now this product, up to power corrections, is nothing but Q squared plus higher order terms in lambda. This is nothing but Q, so you can easily. Is it clear? So remember, n bar dot p is the energy plus the momentum. In the high energy limit, this is approximately equal to twice the energy. The same is true for n dot p bar. So we get twice the energy times twice the energy, we get 4e squared, but the total energy is 2e. So this is E CMS squared, which is S, which actually is minus Q squared. So I did a mistake here, it's minus Q squared. No, I think this was not correct. This is really the absolute value of Q square. Actually, in the process that I'm discussing, Q square is time-like, so there is no minus sign there. This is a positive quantity, and this is exactly what is Q square. So you see, at this point, I'm back here. At this point, I have established this relation. And now we also see how the dependence of Q on Q square comes about. If we had only the single operator without derivatives, we wouldn't have a dependence on Q square. We would just have a single coefficient, C00. But in reality, we can write infinitely many operators with infinitely many derivatives. All these are unsuppressed insertions of large gluon fields. But we can recast this infinite double series as an integral in position space over non-local products of fields. And then using this simple trick that we know the total momentum carried by each set, the effect of all of these non-localities, they can be removed by using shift invariance, and they lead at the end of the day to a Wilson coefficient, which is a function of a single variable, which happens to be Q squared. So this is how the dependence on Q square arises in HQET. And this is completely general. Whenever you do matching relations, you always start out with these non-local structures, and then you turn them into Fourier integrals, and then you get coefficients depending on kinematic variables. You always have to make sure that they depend on this in an RPI invariant way. And in the simplest case discussed here, a single Q square remains. Good. In the literature, these guys are sometimes called label operators. I'm not using that language here. I'm just telling you, when you read about label operators, it's precisely, if you wish, you can see this as an operator whose eigenvalue is the total momentum of the jet. Okay? And it's called the label operator because since you know that total momentum, in a way you can label your fields. You already know what the total energy is. You could, if you wanted, add this as a label to the fields in the same way that we add the label of the velocity to fields in heavy quark effective theory. But I'm not going to use this name anymore. Just if you see it, label operator, that's exactly what it means. No, CV is not a Wilson line. CV is a Wilson coefficient. Sorry, maybe I said Wilson line, then it was incorrect. This is a Wilson or matching, hard matching coefficient. So this accounts for, we'll see. This accounts for hard quantum corrections at one loop order or two loop order. So at tree level, all we got was these Wilson lines. But once we go to one loop, there will be real hard gluon corrections which build up this coefficient. We'll see in a moment what they are. At tree level, it's 1. This thing is 1, and then it will get corrections at order alpha strong. We will calculate it now. if the gluon is hard. That's exactly what goes into the CV. So what goes into the CV would be something of that type with a hard gluon. That would go here. Virtual hard gluon correction. Good. So this was the first half. Now we come to next chapter, the Sudhir form factor. Yet again, in SCET. So I'm going to return to this problem we studied earlier, the quark form factor of shell, right? P square less than 0, and some big Q square here, much bigger than P square, massless. And I'm now going to calculate it from, so this is now in SCET, this is the matrix element, the quark matrix element of this operator, CV of Q squared times C bar W 0 gamma mu perp WC dagger CN 0. Right, so the matrix element of this guy at one loop order should reproduce the one loop Sudhir form factor. So let's just, we have done the Sudhir form factor in QCD using the method of regions. That is how we got inspired to construct SCET. Now we have SCET. Now we should check that we actually reproduce the results for the Sudhir form factor. So I will do this. This is like the region analysis now, except that now we really do an SCET calculation. Okay, at one loop order. So at one loop order, we have two contributions from the collinear region to the Sudhir form factor. Again, I hate this. I have to do these dashed lines for the collinear quarks in SCET. So here they are. This is the current. The incoming collinear quark has momentum P1. The outgoing anti-collinear quark has momentum P2. And now there's two ways of doing a collinear loop correction. One of them is something like this, which would be wave function renormalization. I'm going to take care of this separately later. If I don't want wave function renormalization type contributions, normally we just have the option of connecting the gluon from here to there. But that's not allowed. I cannot attach a collinear gluon to an anticollinear particle. That vertex does not exist. However, remember I have collinear gluons in the Wilson lines. And the Wilson lines sit here at this vertex where we have this operator. Right? This operator is the cross up there. And here I have a collinear gluon. So I can draw a diagram where the collinear gluon goes into the Wilson line. Then I have loop momentum K here, and here I have loop momentum K plus P1. I will work in Feynman gauge. And this time I will not ignore numerator structures. I'll actually really compute the thing. Not in a simplified version, I'll really compute it. Well, kind of. I'll show you how it works without too many details. So this collinear contribution, this is the one exception to the rule I mentioned yesterday that we never use Get-Feynman rules. We'll use them once just to see that they work. So now I'm really using the rules that we wrote down yesterday. So I have my loop integral. I have now I also have spinors in SCET, so I label them with subscripts n bar and n. gamma mu perp. So I start here, external spinner, gamma mu perp from the vertex. Then I have this quark propagator. The quark propagator is n//2 I n bar k plus p1, k plus p1 squared plus I0. Now I have the vertex here. And remember this collinear, and sometimes people do also a dashed line through the gluon to show that it's collinear. The vertex was a monster in SCT. GS times color matrix, and now I get 4 terms. N alpha plus gamma perp alpha P1/perp over n bar dot P1 plus P2/perp gamma alpha perp. Oh, no, sorry. Already made a mistake. K/perp plus P2/perp gamma alpha perp over n dot K plus P1 minus n bar alpha K/perp plus P1/perp P1/perp divided by dot K plus P1 n dot P1. And now I get an n bar slash over 2 times U n P1. Now I also need the Feynman rule for getting a gluon from the Wilson line. Yesterday we had that Feynman rule. The only difference is yesterday the gluon was going into the Wilson line. Here it comes out. That gives a sign change. So that's why I get an extra minus sign here. TA minus G times, yeah, I have to be careful with this spinner, it needs to come later, sorry, minus G times TB times n bar beta over n bar dot K. So this is the Wilson line matrix element. And then the gluon propagator over K square plus I epsilon, and then finally UN of P1. Okay, so you see it's quite a monster. Often things get very simple then when you look at the expression long enough. So let me see. I forgot, okay, sorry, I forgot the G alpha beta from the gluon propagator. So this G alpha beta is important because we have an n bar beta here and we have an alpha here. However, if we contract n bar with this expression, here we get n square, which is 0. And here we contract n bar with a perp object, which is also 0. And likewise here, and the only term that survives is this guy. Okay, so you see this complicated vertex of SCT, at least in this example, it doesn't really enter. When the dust settles, you get minus ICF, 2 powers of coupling, the color factor is CF. We get a U n bar of P2. Dirac structure that survives is gamma mu perp, and then n/n bar slash over 4 times U n of P1. Then we get an n dot n bar from the contraction of this with this guy. N dot n bar was 2. simply. And now we have a loop integral, which is not too difficult, which has k squared plus I plus I0, k plus P1 square plus I0, and here n bar dot k. And upstairs we have n bar dot k plus P1. And yeah, you can, so this is the example, this is the result one gets. If we multiply this with n dot P2 over n dot P2, which obviously is 1, but if we just multiply with n dot P2 upstairs and downstairs, then you can rewrite these two terms with the n. So this n bar dot k1 plus p1 over n bar dot k. If we multiply with n dot p2 upstairs and downstairs, we can write this as 2k times p2 plus 2 p1 minus p2 plus divided by 2k dot p2 plus. And if you ignore this term, you see this term is simple because it simply cancels between numerator and denominator, and then you get an integral which is trivial to do. It's an ordinary QCD integral. This is the term we didn't have in our toy example because we neglected the numerator structure. The second term and this denominator, when you go back to your notes, is exactly what we had in the toy example. So this term was absent in the toy example simply because we ignored the numerator structure. But this term is exactly like what we found when we did the analysis in region. So the point here is that, and this is the one that's non-trivial because it has this linear denominator. So the point here is that the SCET-Feynman rules, they give you precisely back what you get in the corresponding region. If we had done the region analysis also for the numerator, we would have gotten also this term. Okay. Actually, let me, in the notes you have the result for this integral, but let me not bore you with that. Let me just point out this is Pn, which we can set to 1 here because it's already contained in the spinner. And then we get, you know, the anticollinear spinner gamma mu bar times collinear spinner. That's the structure we should find. And the rest is just the loop integral. Okay, and of course the anticollinear contribution works exactly like that. So let me, and it's also in the notes. Let me just focus on the ultra-soft contribution then. The ultra-soft contribution is interesting because now the tricky multipole expansion that we discussed yesterday comes to play. So now for the ultrasoft, we have a single diagram in SCET because the ultrasoft, remember, is the mediator between the collinear sector and the anticollinear sector. So the diagram that we have is this one. This is an ultrasoft gluon now. Momentum K, and then the momentum here are K plus P1, and the momentum here are K plus P2. But actually, this is not correct, the way I'm writing it, because remember, momentum is not conserved at these vertices. We are only allowed to propagate the component of K that is of the same order as the corresponding component of P1. So here, this is only the plus component, and here it's only the minus component, which we are allowed to propagate. And again, we work in C equals 1 gauge. And yeah, this I want to write out in detail because this is a bit unusual now. So here again we have now an integral over the ultra soft loop momentum. Spinner UN bar of P2, IGS, TA, and now remember the Feynman rule for the coupling of the ultra-soft gluon to the anticollinear gluon is proportional to n bar alpha times n slash over 2. So that's the coupling here. Now we have the propagator. The propagator is n bar slash over 2 times I n times k minus plus p2 divided by k minus plus p2 squared plus I0 gamma mu perp times, now we come here, this propagator. This is now a collinear propagator, so it contains n slash n bar times k plus p1, k plus p1 squared plus I0, gluon coupling IGS TB and beta n bar slash over 2. The spinner UN of P1, and now the gluon propagator minus IG alpha beta delta alpha beta divided by k squared plus I0. Remember here that k minus is n bar over 2 times n dot k. No, sorry, I did it wrong. K minus is n mu over 2 times n bar dot k, and k plus is n bar mu over 2 times n dot k. So here we multiply k minus with n, but k minus points in the n direction, so that term vanishes actually, and it should better vanish because n dot p2 for an anticollinear momentum, that's the big component, and k can only be small because it's ultra soft. So this better vanishes, otherwise it would be a power correction. Okay, but this term actually does not contribute. And likewise here, n bar dot k plus also does not contribute because k plus is proportional to n bar. And again, if this was not true, it would be a power correction. So you see that it all works out. There are no power corrections here because we constructed the Lagrangian in such a way that we get homogeneous power counting. So now if you collect all factors, you get minus I CF GS squared U n bar P2, now a bunch of n slash matrices n slash over 4, gamma mu perp n slash over 4 times un of P1 times n dot n bar, which again is 2. And here, this is Pn and this is Pn, but all of these Pn's we can set to 1 because there's already a Pn included in the definition of the Xi spinner. So Pn acting on Pn has no effect, and it also commutes with gamma mu perp. So all these Pn's we can replace by 1. And then again, we get the structure with just the gamma perp, which is the correct Dirac structure. And now the loop integral that one finds is k squared plus I0. K plus, remember, k plus and k minus squared are 0. They are null vectors. So I can write this out. And I find 2k plus times p1 plus p1 squared plus I0, 2k minus p2 plus p2 squared plus I0. And upstairs, we find n bar dot p1, n dot p2. This is q squared. And down here, instead of k plus p1, we can use that this is the same as k dot p1 minus, and k minus p2 is the same as k dot p2 plus. And with this results, you can go back to your notes and you find this is exactly the ultrasoft contribution. There are no numerator structures in this case. So this is exactly the ultrasoft integral. And you see that the multipole expansion, which was so strange last time, it gives exactly rise to these linear propagators as it should be. There should not be a k1 squared term because it's power suppressed, and the multipole expansion makes sure that this is the case. So in the notes, you find the results for all these contributions in great detail, but let me just not write them down here. I will give you the result for the sum of all terms in a moment. So the only thing left to do is wave function renormalization. So wave function renormalization. Well, wave function normalization just tells you that while at tree level what we get is simply this structure that we have also seen over there over and over again. If you include wave function renormalization, you get square root of c for each external particle. So we have a quark and we have an antiquark. They, of course, have the same c factor. They are each other's antiparticles. So essentially, we get CQ to the power 1. And since we do the off-shell Sudakov form factor, you also need to do the off-shell wave function renormalization, which is not normally what you find in textbooks. But the off-shell wave function renormalization, let me just give it to you. It's 1 plus CF alpha strong over 4 pi. And then, you know, there is a UV pole, 1 over epsilon. IR divergences are regularized by p square. And then there is a constant here. And I was too lazy to compute the constant. I just call it C because it will cancel out at the end of the day. There's some constant here from wave function renormalization. And of course, you know, p square here is either p1 or p2, depending on which of the two quarks we look at. Now, we put everything together, collinear contribution, anticollinear contribution, ultrasoft contribution, wave function of the first quark, wave function of the second quark, okay? And then we have everything except for CV. And we can also put in the CV. So, the total SCET matrix element is now given by, you know, CV of q squared times outgoing quark P2, C n bar W C bar of 0, gamma mu perp, W C dagger, C n of 0, evaluated between quark states with momenta P1, P2. Okay, that's the total SCET matrix element. And what we find is this is CV of Q squared times U bar n bar P2, gamma mu perp, U n P1. And now, I should have written it up there. Let me just say 1 plus da da da, and the da 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 is a CF alpha S over 4 pi times a correction, and the correction I give here now. What is this correction? If you put everything together, 2 over epsilon squared plus 2 over epsilon log mu square over, now I introduce again capital P1 square, which is minus little p1 square, remember, plus log of mu square over p2 square. Now clearly this is the collinear contribution plus wave function renormalization. This is the anti-collinear plus wave function renormalization. Now comes the ultrasoft. Plus 3 over epsilon plus log squared mu squared over p1 squared plus log squared mu squared over p2 squared minus log squared mu squared q squared over p1 squared p2 squared and more, 3/2 log mu squared over p1 squared plus 3/2 log mu squared over p2 squared plus 8 minus c minus 5 pi square over 6. Okay, that's what we get. It looks a little bit different from our toy example because, for instance, we didn't have these single logs, and the reason is that we didn't include the numerator structure completely. This is the exact result. Yes. Which term cancels it? There are these p's all over the place. Yeah, remember that the big P is minus the little p. That was just not to have minus signs under the logarithms. So, you know, if you really care about IR versus UV, and I think Anish already told you that you shouldn't because you just confuse yourself. But you can think of all of these poles as ultraviolet poles now, because now we are in a low energy effective theory. We have an infrared cutoff, the off-shellness. So all the divergences are UV from the point of view of the EFT, okay? And then there will be infrared divergences in this coefficient, in the Wilson coefficient, because in the Wilson coefficient, the low energy modes are cut out, so nothing saves you in the infrared. And then the infrared poles of this guy and the ultraviolet poles of this expression, they will be in one-to-one correspondence, okay? But it's sometimes more confusing than helpful to think in that way. So I actually finished on the minute. This is really, believe it or not, this is the end of the first lecture. This is not the end of the calculation because it's a divergent result, right? We don't want a divergent result. But now in the context of effective theory, what we need to do is we need to remove these poles by renormalizing our operator. This operator, we need to renormalize this operator so its matrix elements are finite, okay? It's not enough to say that, well, there was also a hard region in the region analysis with poles that cancel these poles. Yes, that is true, but we are not doing region analysis here. We're doing EFT. We have a matching coefficient, it's well defined, it's free of poles, and we have an operator which is at this level a bare operator, which we need to renormalize. So after the break, that's what we'll do. We'll remove these poles with an ultraviolet renormalization of the SCET operator, and that has the advantage that it gives us for free the renormalization group equation for that operator, the anomalous dimension, etc. Okay, so we'll talk a lot about renormalization group and such kind of things in the last lecture after the break. I'm proud that once I finished on time. I was not expecting that. You see that also. You see here, ignore the divergent terms for now. You see there are logs with the collinear scale and there are logs with the ultrasoft scale. So this theory, this matrix element without this factor, which is of course the hard physics, this matrix element basically knows about the collinear scale and it knows about the ultrasoft scale. And these two scales are not the same. So actually, there's no choice of mu that would make all of these logarithms small. Since the low energy is here, so at the moment, think that mu is somewhere here, and then there is q square up here, and that part of the physics we have put inside CV, which will be a function of mu and q. And the SCET describes you, the matrix element describes you the physics down there. This is the way how to look at this. And of course, you see that there are poles associated with the collinear scale and poles associated with the ultrasoft scale also in the structure of the divergences. So sometimes in SCET, we'll come to that later, one factorizes these low energy matrix elements into a collinear part and an ultrasoft part, two separate entities, but that will come in the next lecture. This is not a complete factorization yet, right? Because we have three scales. It's not enough to factorize hard from the rest. We have to factorize hard from collinear, from soft, ultrasoft. Then we have complete factorization. Please. Yeah. Sure, you can always make things more complicated. Let's do an intermediate step. Instead of the photon, I could have a W or C boson, for instance. And that would actually be very relevant. That would be like, for instance, Drell-Yan production. You would have quark, antiquark go to C boson or W. But of course, you can also generate jets from the decays of heavy bosons. That would be completely analogous. Now you say, what if it's a colored particle? If it's a colored particle, there's also color before. The gluon comes from somewhere, right? So you need to be careful then. I mean, either the gluon, well, no, the gluon would be a hard gluon. So then you really have a hard process. Let's say you take whatever, 2 partons out from your colliding protons, then you make a gluon, and then the gluon makes 2 jets, right? So this is now, this is an underlying hard function. It's a, let me see if I can do that here. So for instance, there we would have a hard process that here we have a proton and here we have the other proton at the LHC. We pick one parton from each, we do some hard scattering, and we produce, let's say, a pair of quarks or gluons that we call jets. Okay, so this would be jet production at the LHC. There's also stuff going down the beam pipe here. And now, in a way, this hard function would be your external operator. Okay, and now in this hard function, you would introduce for the protons. So, for instance, you would describe this guy by some collinear, if it's a quark, by some collinear spinor Cn, and this guy by some Cn bar, or C bar, N bar. So you would call these collinear and anticollinear. That's now the beam direction. But now the jets go something like that. Okay. So now you have another direction. So let's say we call this N1, but N1 is not the same as N or N bar. Okay. And then now we could call this either N2, or we could call it, in this particular case, N2 is N1 bar, but it's, you understand, I mean, you have back-to-back the beam axis, and now you have back-to-back the jet axis, okay? So, and now if these are also quarks, you would have, you know, you would have other collinear spinners here in the directions N1 and 2, and maybe you also get a gluon out here that defines some N3. So at some point it becomes easier to just label the directions and forget the bar. And now this would be an operator containing 4 or 5 different types of collinear fields. And that operator for itself, then color is conserved. But you're absolutely right. If I start with a colored particle, I mean, it doesn't come out of the vacuum, right? It comes from somewhere. Yes, in fact, the Wilson coefficient here is really the hard scattering amplitude, if you think about it. Because everything we are interested in now is what happens to these jets, right? So now these quarks, they start to radiate somehow. They build up some, you know, some jet cone here. Then maybe you have another jet here. Maybe you have some, you know, you can have some ultra-soft emission into the region between jets, because between jets usually some radiation is allowed, etc. But you also get the feeling this is infinitely more complicated than what we are discussing here. So there is a huge step from E plus E minus to proton colliders, simply because you start with colored objects in the initial state. And the techniques are still the same. You can have 3 or 4 collinear sectors. The ultrasoft will still interact simply with them. And in the last lecture, we'll see that we can decouple them using field redefinitions. That will all still work. But you know, for instance, your hard matching coefficient now will not just be a function of Q square. If it's a 2 to 2 hard scattering, it will be a function of STU, of the Mandelstam variables. If it is 2 to 3 scattering, will be yet more complicated, okay? So it's, but again, I told you yesterday, you have to distinguish between conceptually difficult and technically complicated. And this is, to a large extent, the tools we have already developed, they are more messy. The context is more messy. You have to work harder here. And there are also some new complications which I haven't mentioned. For instance, related to things such as Glauber gluons, etc. But I mean, in principle, you can attack such kind of processes using the technology I have described, but you will have to introduce more collinear sectors, more than just 2. Necessarily, because the beams are your first 2 collinear directions. So if you produce anything colored, it's 3 or more. If you just produce Higgs, or Higgs inclusive, Higgs plus X, that's a classic application of SCET. Then the collinear fields are in the initial state, and what you produce is a heavy colorless particle that's like virtual photon to QQ bar, only backwards, if you like. Gluon producing a colorless Higgs. So Trelian type production, that was the first SCET applications in collider physics, because it's the simplest. It basically, the matching calculation that you need is this one. If it's quarks, it's this one. And if it's gluon, there is an analogous definition of a combination of Wilson line and a gluon field that gives the gauge invariant definition of the collinear gluon. Yeah, thanks for the great question. Thanks for the question.